Okay, I think we're good to start. We're doing hash layers for large Sparse models. This is a paper out of FAIR in 2021. The basic claim is that rather than doing RL loss or top K or top 1 routing, you can get equal or better results by simply routing based on which token and which token was originally at that index. So you don't route based upon the current activation, you route explicitly based on which token was at that index in the input. Most comparisons are against switch transformers. There's a very brief comparison against base layers. But for the most part, all of the one-to-one comparisons are against their implementation of switch transformers. The biggest comparison is on Reddit data. They're very vague about the difference between dense and sparse parameters, but I believe the model is always a 222 million dense model that they have added experts to. This token count also is approximate because, as Maine was noticing, there is there's an implicit GPU factor that maybe multiplies this, so it's possible the token count is much higher. I think it's a relatively small test either way, but it is obviously better if the low data size is not the reason for any of the results we see. Pretty much all of the heads-up comparisons it makes, it wins. It does lose the 5x16, so 5 layers with 16 experts per layer. It does a little bit worse. It has no auxiliary losses, and it is incredibly dumb. But dumb is good because dumb is hard to fail. Oh, and doesn't compare against SOF, MoE, or expert choice because they're newer than 2021. So switch layer on the left for basic review, hash layer on the right. Switch layer is applying a linear function and taking argmax, it's top 1 routing, because as long as you have auxiliary loss, you get even distribution. As long as you have auxiliary loss, you get even distribution, and you drop any tokens that go over your limit and just assume that you will you have a learned function that decides which input goes to which expert. Hash layer does not do this. Hash layer simply takes the input token and chooses an expert based on this. Something that they do not explore very much at all is that we are hashing the input token, not the activation. And what this means is that the same token will always go to the same expert index at every layer. They only have a couple of tests with multiple hash layers, so they don't explore this in a lot of detail, but it seems like an important difference. A switch transformer, any given token can touch any given combination of experts. In this case, a given token can only go one path down the experts. But it's still, the fundamental idea is that it is an incredibly dumb routing algorithm. It's a routing algorithm that effectively makes one choice and never changes it. As far as exploring the difference between different routing per layer and routing directly through, they explore it exactly once. It's mentioned once in a table and never in the text. And it's simply that with their 5x16, if they route to a different expert per each layer, so you apply a different hash for each layer to choose an expert, instead of applying one hash and choosing an expert index that you then use for all layers, you get this slight improvement. It seems actually extremely important as a difference to me because you end up with effectively totally parallel experts that never interact with each other except through self-attention if you use the same index for every layer. But they don't seem to have thought about this very much, and they don't talk about it at all. So that's my number one ablation that I wish they had done that they did not do, is more testing with this and more figuring out how much it matters whether expert indices are always the same or expert indices are different. Oh, and if it turned out that expert indices always being the same was better, it would actually mean that you are better off having essentially n parallel experts versus having a lot of different versus having expert layers where every expert layer can talk to every other expert layer, or every other expert on every other layer. Does all of this make sense so far? Any questions?
I don't think I actually grasp what goes on for the different hash.
Oh, so for for same hash, you do a hash once during input, right?
Yep.
So I've decided that my token goes to 246, and I route it to expert 246 at every expert layer.
Yep.
Assuming there's that many experts. At different hash, you will apply a different hash for each layer. So it looks more like a switch transformer, where for a given token, it can go to any given expert index on any given layer. It will
Okay,
go
but
to
the
it will
the
go to the
hash
same set of experts each time. But yeah,
the hash is ultimately still based on the initial input token
yes,
for wave, is that right? Okay.
yes, it's still based on the initial input token, and it will still be invariant. It will never change, right? So instead of having with this setup, which is their default, essentially every bucket is a set of layers, and this set of layers, or this set of experts, will always see the same set of tokens. It will never see none of these experts will ever see any of the tokens that are not in this bucket, right?
Yep.
So it's essentially a totally separate model, or very close to a totally separate model, where it's coupled by attention, but it never sees, none of these experts ever touch any of the other token buckets. Whereas if you multi-hash per layer, you get essentially each token has a unique path or a close to unique path where it chooses a different expert at each layer. Now that token will always have the exact same path. That path is invariant, but they're in this case the number of possible paths is just the number of experts. Whereas if you multi-hash it, you get a number of possible paths that is equal to the number of layers times the number of experts per layer, and each token should have a unique or almost unique path. Does that make sense?
Yes.
Yes. So these seem like very, very different setups, but they did not seem to explore that very much. I think their baseline was to establish if hash worked at all. So finer details like whether that you had set buckets that all had one path or whether each token had a unique path were not majorly explored. It was very frustrating that this was only one table. But I think that they were focused on establishing that hash routing worked at all. So different ways of doing hash routing like this, I think they were less interested in. The basic scorecard is what the actual training setup looks like. They have a lot of these tables, and so I tried to resist pasting all of them into the slideshow. Essentially, at every configuration, hash wins except the 5x16 where it's a little bit behind switch transformers. If that makes sense, it has slightly worse loss. Parameter counts are misleading. The dense parameter count is 222 million. They're counting sparse parameters as if they are dense parameters, which is very difficult to read ordinarily. They're
Do you have
not
any
counting
idea if they're
parameters separately.
using the most optimal hyperparameters and the rest of the setup for the switch transformers that they trained?
So for this one specifically, they changed their load balancing loss, but I think almost all of those will be default. Where I
Right.
think they have some of them listed somewhere, but I think almost all of them are default from the switch transformer paper.
Makes sense.
Which I think also from the perspective of 2023, there are a number of small tweaks. I think there's Z loss and a couple of other things you can do now. So it's not guaranteed that this is a heads up trend. If you went and got this hash layer implementation, I think it would lose against even current switch transformers, right? If you did a switch transformer with a well-tuned Z loss and the other things that people will do with it now, I think the switch transformer would actually beat hash layer in this comparison.
Yeah, that makes sense.
These are their nice loss curves that show that hash is better. Or, sorry, perplexity here, and perplexity by number of experts on layer 7 of the 7-layer decoder. The other non-parametric routings they did were all done with 1 times 64. So one expert layer with 64 experts. I think that there is probably a fundamentally different case between having a single layer and having multiple layers. So one of the things that seems underexplored is the 5x16 configuration they had. So you have 5 layers with 16 experts apiece. Those actually seemed more interesting, so that seems underexplored. To try to summarize all of the several pages and this table that are about this, one of the interesting results is that clustering similar tokens into similar buckets does not work. So if they do k nearest neighbors clustering on tokens, and then assign every bucket or every expert index to a similar set of tokens, it actually does not work if they go back to assigning it out randomly, or sorry, back to assigning it out sparsely. So if you have a given bucket, a given cluster in your tokens, you assign the members of that cluster to different experts as much as possible, you get back to essentially the same performance you have when it's random. And that is token clustering is worse. Dispersed hash, where you disperse things across a cluster back, gets all the way back to where we got with balanced assignment. Fixed random assignment loses to balanced assignment, but by very little. It doesn't seem very important. That basically you get a closer to uniform distribution across buckets if you use balanced assignment, but you still have outliers that mess it up because some tokens are exponentially more common than others. So if a given bucket has a couple of the most common tokens in it, it becomes impossible to balance. So even their balanced assignment is not actually that well balanced, it's still fairly outlier heavy. Balance is a little bit better than fixed random. Clustering tokens affirmatively hurts performance, right? Other small experiments are distributing according to bigram, so current token and previous token. They suspect that this creates too many buckets, so you cannot learn from it. That is specifically, so if you have a vocabulary of 20,000, if you have a vocabulary of 20,000, the number of possible hashes is now 20,000 squared, which is a ridiculous number. So any given expert may only have seen a specific input once, or a specific token once, right? So it doesn't work very much at all if you use bigrams. Routing according to previous tokens sort of works, but not really. Like, it harms performance, but not back to baseline. Routing according to absolute position brings performance all the way down to baseline. You might as well not have sparse layers. And oracle routing, where you route according to the known output, which lets it cheat, achieves like absurdly low perplexity.
There are a lot of decisions and observations that have been stated in the last 3 slides that I wonder if they will hold up for increased scale. Like,
Yeah.
the first thing that I did see is that when you noted that clustering similar tokens does not work and actually leads to worse performance than trying to separate out the similar tokens as far as possible into different buckets. Like, part of me wonders how much that's attributable to the transformer that they used for clustering, and
Yeah.
like whether if you had, let's say, a transformer that was of a similar scale to the hash model being trained itself, or if you used a much bigger transformer that had a much better representation of the tokens, if that clustering would work better. That's for this slide. Then
Yeah.
on the next slide, okay, actually, if you have a response to that sentence, then please say so, because I forgot what I was gonna say.
Okay. Just the other thing that's obvious to me is that this is a 1 by 64, so they have 64 experts, which is a respectable number, but they only have one layer. So all of these ablations with the type of routing do not take into account. They're all in an opportunity where the experts don't get to interact with each other, right? You have only one expert layer, so you cannot perform any conditional computation under this regime. So the earlier thing about how it seems like an under-considered decision was between routing along basically swim lanes or letting each token take a unique path. It's possible that swim lanes is better for clustered tokens and unique paths might be better for non-clustered tokens, but we don't have enough information in the paper to actually get at that. So I could see this going the other way based on different configurations. It's not an extremely strong result for a lot of these.
Hey, so I was really late coming in. So with this routing, the the hash selects a single expert per layer.
It selects their baseline is actually they select a single expert index, and they will select that expert index at every expert layer.
So one thing I would be really interested to see is what happens if they stacked hashes, because that was how the hashing trick used to work in earlier NLP, was you could construct multiple hash functions. So you would deliberately induce superimposition or
That is
superposition.
their part 3 of their paper, right?
Okay,
Yeah.
cool.
This is okay. Yeah. So there's this one where they use different hash functions per layer,
Yeah, but
where
what he's talking about is stacking different hash functions, right?
in the same layer. If I get
Yeah, so it
that
becomes
right,
like a selecting code.
they did do that.
Okay,
It worked. That's the short cheater version of it. Is for a small scale experiment, it worked.
sweet.
Um, let's just
But
skip ahead to that.
what was this? Oh,
This.
okay, yeah.
Just skip ahead to this. This is what they did for single layer multiple hashes. Instead of choosing one linear layer, you stack n hashes, and then you concatenate together n different matrices and declare that you're expert for that token. It also worked, but the scale was very small.
Yeah,
So
it
go ahead. Sorry.
does seem like it would be difficult at the very least to implement their concatenation of separate
Well,
subsections of each linear like expert in with their multi-hashing technique, because they need to split each FIFO network into like a series of segments and then concat them during runtime
I
dynamically.
think
It's
current recommendation is to use up to 1,024 experts, right? So if your input size is not much larger, like not at orders of magnitude larger than your number of experts, this just wouldn't work at all, because you'd be coming up with essentially one row or one column of your linear layer per hash, which does not seem viable at all. That
yeah.
seems like it would degenerate really badly. It does work for what they use, but they used up to n equals 8, right? So they're using at most 8 hashes per layer, or 8 hashes to stack together linear transformations per layer.
Right.
I just wanted to add in what you were saying based on certain tokens having exponentially more occurrences.
Yep.
I've kind of, I guess, intuitively been feeling lately that tokenizers need a lot more attention than they've gotten, at least since um, I've been focusing on ML. It seems like they're one of the most neglected areas. Um, and for something like this in particular, it seems like the tokenizer is critical.
Yeah. Man, we keep skipping ahead to things that are on later slides. So this is the actual distribution,
Sorry.
by the way. Oh no, I'm good with it. And also, I'm affirmatively trying not to go on a long rant about tokenizers, because it's a hobby horse of mine. But so this is the actual distribution, if it matters. So this is, if you do random distribution, this is what you get. If you deliberately try to balance your buckets, you get this. These are basically just outlier tokens, right? Like a single outlier token is in each of these buckets, and there's nothing you can do about it, if that makes sense. If you had a
Yeah.
very large amount of buckets, I think this might not be a problem. Or sorry, if you had a reasonable number of buckets compared to your number of tokens, this would be less of a problem, I think, because you'd almost devolve towards 1 or 2 tokens per bucket.
It gets
But
easier
it's
to
very odd.
balance as you have less buckets, right?
Yeah, okay, so
Because
you'll have an easier time balancing around these outliers, but I think it will matter less at higher scale, if that makes sense. Whereas, so this outlier will not be as, if you had a large number of buckets, this would be one specific bucket that looked funny, but it would be a much smaller part of your distribution, if that makes sense.
Yeah, I mean, I've been thinking about this lately. I've brought it up a couple of times, but I'm kind of thinking about something even simpler than hashing, which is just modulo gating
Yeah.
based on the token ID. Because I mean, essentially, in that case, the limit of experts you could have is the size of your vocabulary, theoretically.
Yeah.
But it has me. I mean,
Um,
obviously, then you've got way
that would be
overtraining and
equivalent to
way.
their random hashing, right?
yeah, that would
Like,
be roughly equivalent. Actually, I think Bigram will do you for that. Like, so even if you have a small vocabulary, let's say you had hypothetically a very small vocabulary of 256 and you have thousands of experts, which is not a hobby horse of mine at all. And you have started to run out of expert slots or of hash buckets basically because you have too many experts. You can start hashing. You can start going by bigram by going by current token and previous token. So you
Gotcha,
can,
yeah.
regardless of your vocabulary size, I think you can do this to make sure you have enough buckets.
Yeah, I mean that's
Yeah.
something I need to dig deeper into that because what I've been thinking is for those outlier tokens like just split them among multiple experts, whereas a more regular frequency token would just get one.
Yeah, that would make sense to me. Where assuming that you have sort of a one-to-one correspondence between tokens and buckets, and you always calculate it in the same way, is not necessarily given. It's being done here, but not necessarily. Like really, any function that goes from tokens to buckets is fine. It doesn't actually matter what it is. They will all generally work for the sort of assignment, and hopefully not hurt performance very much. Because I think for all that we see degradation for certain things, like if you go to use future token partitions from a bad transformer or hash on position, like these don't really work, but they don't destroy the model. Generally speaking,
Right.
most of these other modifications slightly change how it behaves. They don't change how it behaves a lot. Like if you looked at these two distributions, you would think these would behave very differently, but they behave almost not differently at all, right?
Yeah, and I mean I think that
assignment is very
comes back.
forgiving. It turns out.
Yeah, I mean I think that comes down to the core reason I think that MoEs work, and that's just over parameterization.
I think that's probably getting to be the default expectation for people.
I mean, I
Just
think that's part of it, but also that uniform hashing is like identical to how people used to apply the hashing trick like way back in the day. So I think part of this is making a statement about how MOEs work, but also part of this is like, hey, don't sleep on old NLP tricks.
Yeah.
For sure.
I feel like we might want to exhume that paper, like whatever paper that was originally done in.
Hashing trick stuff?
Yeah.
Yeah, I'll find some old hashing trick stuff for you.
Neat. Okay. So I think we're here. If I remember where we were.
Yes.
Do any of these other oddball things have obvious observations? Okay.
Well, I mean, like I don't like you were saying that the bigrams don't work because there are some bigram sequences that just appear way too rarely in their training data, and like
I think almost all bigrams will be very rare just because the vocabulary is kind of big. Where I think their baseline vocabulary is that's not the one. Their baseline vocabulary is, I think, relatively large.
They had an AK1 and 32K.
Yeah, they have an AK1. I think most of them are on
and the 51K1. Jesus Christ. They use
Yeah.
Shift-D2's dictionary.
Yeah, they use that for one. It doesn't work because they assume because too many buckets.
That makes sense.
So I think the idea that squaring 8,000 gives you too many different bigrams so that each token will have only seen, each expert essentially will have only seen each token once, possibly.
No.
So you get to the point where there's virtually no expert affinity for tokens, which is problematic because you can't necessarily, you don't necessarily have enough data, almost no matter how much data you have, to have seen any number of bigrams a significant number of times.
So that comes back to something I've been thinking about with the modular gating, and just by slicing it, by remainder being your expert ID, but also I've been thinking about how to have experts see other tokens. And maybe you start out by just training a dense MLP, and then you split that out and maybe make that remainder or that modulo operation an increasingly larger number of experts in subsequent training runs. Just duplicating previously trained experts, obviously, and then training on top of those.
We always want to reinvent cell division.
I added 2 hashing trick papers to the MoE thread.
Sweet. Yeah, the fact that we have effectively 2 chats makes it actually kind of tricky to keep track of.
Yeah. Why does the pop up the meeting window as a separate window, and like that window itself has the chat open on a sidebar, and I overlay that over the main Discord window?
Let's just say that doesn't want to work for me with my current configuration right now. Anyway.
Yeah.
So, to get back onto Rails, they did experiment with the giant dictionary for their Wikitext experiment, although Wikitext is relatively small, so I think it's a weak result. The big dictionary almost reverts it back to baseline. I think they generally have a bias to assume that certain things are just going to be based on the number of buckets, like the number of buckets to the size of their dictionary. Because if you have very, very few items, like if you have a lot of items that are getting routed effectively randomly, so non-repeatably, because a hash is random, but it's repeatable, right? It becomes much harder to get repeats of specific data into specific experts if you have a very large dictionary or if you use bigram hashing or anything like that. So it's not also because all of these are relatively small, where their big test is 128 experts. Since there is sort of a standard recommendation to go up to 1024 for a lot of things. It's not clear how this interacts with the token count issue they have, where if your number of tokens, I think what will matter is the number of experts relative to the number of buckets you have. So for a small number of experts, it will behave probably very differently than for a large number of experts.
I mean, I don't think anyone is using 124 experts in production.
Yeah, I don't think that's currently a thing. This is what we skipped forward to earlier, which is small-scale experiments with multi-hashing, which is basically it works, even though concatenating several matrices together like this seems kind of weird. I think since we actually liked this, we can go get the actual paper for that. It's this, where they're just pushing it against push shift again. Params is, these are not dense parameters, so I would not worry about them too much. This is probably all the 222 million switch transformer with some experts. And broadly adding the multi-hash up to 4 different hashes per layer, so you're going and getting 4 different matrices and concatenating to get them together for each expert's assignment seems to help performance up until about here. It helps a little bit here, but broadly, it seems difficult to see how this scales, just because you end up with a point where when you have a lot of experts, you potentially have more experts than you can reasonably concatenate together of matrices, right, to create your expert layer. Although it's possible I'm wrong. It's possible 1 row per hash is an okay idea, but it seems absolutely insane to me. Yeah, does work at least where they were using it. And yeah, this is only with 32 different, I guess they're not even experts anymore. They're submatrices. So
Yeah.
you have 32 different options, and you choose 8 of them in some specific order in order to do your processing. The fact that it works at all is kind of remarkable to me, and maybe it will make more sense once I've reviewed the relevant NLP literature. Positioning the hash in a layer later seems to work better. Fine-tuning works unless you freeze everything but the experts. They guess that's because most of the capacity of the model is there, but I think that's just a blind guess. An odd switch transformer thing is that switch transformers, at least in their configuration, works better if you use the token and not the activations to route. Where I think the original switch transformers is actually routing on activations,
Yep.
You basically just take the input before the activation. This also, I don't know if I'm seeing it in my head incorrectly. This would also have a parallelism gain because you could make your routing decision at the same time as you were applying activation, right? Like while you're applying your Geglu or whatever, you could at the same time be doing your routing choices in parallel. So I think you would actually get an inference time speed up or a training time speed up, just because that becomes a parallelizable operation.
Yeah, in general, this paper tends to neglect the performance implications of hash
Yeah,
routing, I guess. Like it's not entirely clear to me that they even get a balanced number of um, tokens per expert in like each of their training steps here, because like the distribution of tokens for their expert is good across the entire data set, but not not like per sample, right?
right. So yeah, it's not entirely clear if you have a given sample that's very, very heavy on on a specific 5 tokens, and then you would completely max out that specific expert, right?
Yeah, I'm thinking like if someone just sends a batch of like pure A's to the model and you have
Yep.
no like expert capacity to drop the tokens, then you just go OM.
I mean, I think I'm trying to think what you could do with that. I think if you're actually holding them all in memory, it's a problem. I can see a couple of ways to try to fix that, but yeah, fundamentally, if you have,
You could try the adjust like shuffle the data set such that you always have balanced data like ahead of time, but
Mhm.
I'm not sure like if that would affect the training, right?
Yeah. Oh no, I'm just thinking you could, if that came in, you could possibly just load the different expert layers, since the expert layers are so they're very predictable. So you could possibly just in time get your like grab your expert layers, because
I
if you
mean,
know you only need some
realistically,
of
at
them.
the larger batch size of like let's say 2,000,
Yeah.
then you're always gonna have all of them loaded.
Yeah. Fair. Oh, I just think I
I
don't know.
think
It's an odd question about how you distribute workout. Go
Yeah.
ahead.
I think in terms of resource usage, I think with the rise of techniques being applied to MoEs, I think this is obviously with any MoE approach. I guess if you can get those adapter layers quickly loaded and unloaded, then that can make a huge difference. But especially
Yeah,
with
but
something like this
that would like defeat the whole point of.
that's already just
I think
using kind of a dumb routing.
the way I see this being better for specifically that is that because you know what layers you need as soon as you see the input token, you effectively get more time. Whereas with an actual parametric routing, you don't necessarily know which expert layer you're going to.
Mm,
Yeah.
Right. You don't know what
Yep.
expert layer you're going to until like right before you need it. Whereas right now, like with this specifically, you would know exactly what capacity you needed for each expert layer for the entire model. And especially if your expert layers are
Mm,
not on your first couple of layers, you effectively have like forever in computer time to go get whichever layers you need and make sure they're spread out the correctly. So I
right.
suspect that being non-parametric, meaning that you know what layers exactly you need as soon as you see the tokens, you might actually be able to just get around that completely, where you can hot swap layers a lot less. You can hot swap layers with a lot less need to be very, very correct about, or need to be very, very fast or very, very smart about it, because you
Yeah.
know in advance what
I
your
think
capacity is for each one.
I think also this mitigates
Your
a lot of the overfitting risk.
your audio's in and out for me.
But he was saying that it
Oh,
will
I was
mitigate the
saying,
overfitting risk.
Oh yeah,
I mean, I'm not actually sure how it would how it does that, but
I think the
well,
main,
just
you don't have the risk that one expert and only one expert gets data, because which does mean you don't need auxiliary losses that
true.
can mess it up.
Yeah, I think it's kind of like dropout, but in the other direction.
Yeah.
Drop in.
Yep. Yeah, you never know which layer exactly matters right now. The base layer comparison, they say it wins. Their base layer comparison tells you almost nothing because it's barely mentioned in the paper, unfortunately.
I think it will be more difficult to apply this technique to achieve some form of like a hit of time loading than you're expecting it to be, because I don't see how in, like, let's say an average sample of, I don't know, 512 tokens, like, in all likelihood you are going to have to end up loading all of the experts, right?
Yeah, probably. But you should know all of their capacities. So if let's say half of that is just the letter A followed by a space, which is a token, which of course it is. I know in advance, as soon as I see the incoming string, that I need 256. I need a capacity of 256 for that expert, right? On every layer where it appears.
Yeah, but the baseline efficiency is having is that, like, in a switch transformer, your inputs are almost always going to be balanced, and you are never ever loading in and out an expert.
Yeah.
Whereas for this, like, let's say you discover, oh, okay, I'm going to have really a lot of tokens for this particular expert, and it's going to bust the GPU out of memory. Then, like, what do you even do? Then you need to load that onto a secondary GPU, and
Yeah, it's true.
that's not going to be faster.
I think it
Like,
does. It does depend. It's basically okay. It's entirely if you can do it to the side while you're not doing anything else, right? Where you would otherwise be waiting for propagation through earlier layers.
yep,
It's possible you could have have a different machine that has one copy of that expert layer ready to go that basically evicts everything else and makes sure it has a giant broadcasted copy of that expert when it needs it.
true.
So like I could see that working, but it would be very, very tricky. Whereas I think you could have if you had almost the same problem in switch transformers where you have suddenly one expert, like someone has managed to poison your data and you have a whole lot of a specific token, you won't know that you'll still have that problem where I guess you'll drop it, but you won't know that you need that specific expert until that specific layer runs that routes every single token to the same expert, right?
Yeah.
So I think it might be a little more viable to do sort of a hot load of a layer here, but it's hard to call without very, very specific details for an implementation.
Yep.
Because I guess also if it is blazingly fast, that means you have less time to do a memory fetch or less opportunity to broadcast out or any of that. So it's actually more robust if your existing setup is, I think, slow.
Also, I think part of the gain is that with MOEs, any given layer like can be kind of smaller, right? Because instead of having one really wide layer, you can have you can factorize it into multiple experts. So I think that means that the VRAM for inferencing goes down. So although you won't necessarily have the gains of hot swapping different chunks in and out of memory, you'll have a lower like RAM footprint for inferencing still, won't you?
You need hot loading in order to get a lower VRAM footprint. Otherwise, the total number of parameters that you have in memory will always be less VRAM efficient than an actual dense model. And
I think
Right, but I'm not talking about the number of parameters in memory. I'm talking about the size of the matrix that you'll get when you're doing your forward pass, that the activations.
Yeah, I mean, so for a reasonably sized batch where you use at least each expert at least once, I think it's supposed to be identical. That's sort of the advantage of sparsity, because you were going to have to, if you had one dense matrix that was of size n, you still have to multiply that across every input. Whereas if you have I don't know, 1,024 matrices, and you multiply each input by one of them that you have chosen, you have the same amount of space taken up. So across a batch, sparse MoE is identical, or
Okay.
intended to be, assuming that it's balanced. With no batch, it's not identical at all, because you have to go get these 1,000 some odd experts and then only use one of them, right? So it's much, much, much worse. It only actually works as we do it now anyway. It only actually works as a reasonably efficient comparison to a dense model if you're amortizing it over a very, very large batch where you utilize most or all of your experts.
Okay. Cool.
Yeah, it's
I just
a
want to
weird
shout
point.
out.
Go ahead.
I just want to shout out that you got your free bird in there.
Oh yeah,
First sub bullet point.
yeah. No, if
I
if
love it.
if we can dig T5 each time, I'd be very happy about that. I don't even have anything against T5. I just think making fun of it is funny. Like it's a perfectly respectable model. It's just like more than a year old, but it is amusing to complain about it constantly. Yeah. So my wishes would be more scale, more than one layer, decoder only, more different hashes, and more figuring out what on earth is going on with tokenization with this, because the tokenization interacts with it very oddly, right?
Yeah.
If you just assumed hash layers work and you do whatever seems like it works and your tokenization is a little bit different, it's possible it breaks the whole thing. So it's not something they explored in a lot of detail. Probably random but stable is fine. It's not terrible, at least. And I guess my most optimistic takeaway is, given that there's been a lot of refinement on switch transformers, but not a lot of refinement on hash, it's possible hash is just uniformly better if you figure out the best way to do it. Because it does work when it doesn't seem like it should work at all. So the fact that it does work and that it has very little research on it, it seems like it could be a generally good choice for some things. And you also get the benefit of there's no hyperparameters that might make it unstable, and it's generally more efficient. Yeah.
What bothers me is that, so in this paper we observe that clustering similar tokens together is bad, and
Yep.
that the hypothesis is randomly distributing the work across multiple experts just leads to better performance because of sparsity and, like, I don't know, faster learn representations or something. But
Yeah.
like, if randomness is good, then it's very hard to explain the results of other routing algorithms that perform better. Like you see, I posted the screenshots from the unified scaling laws paper in the MoE reading group thread, and like over there they find significantly that S-based routing and RL-based routing perform better, and like those are definitely not random. They're definitely not doing
Yeah, they're
random
very,
things.
very, very opinionated.
Well, I think that just
So
means that it's a different mechanism, right?
I mean, even here, the takeaway isn't that it doesn't work if you cluster it; it's that it works a little bit worse. If that makes
yeah,
sense. So I could see it depending a lot on exactly how your routing, essentially being very, very detailed. That very much depends on what exactly it is switching on. Where it's possible a clever routing algorithm, even though it will tend to put similar things in similar places, might be very, very choosy about, like, it pays very close attention to a specific index when it makes a routing decision. So even though it might be a globally very similar input, it might have become very clever about knowing that these two very similar things, if they differ on this one specific criteria, you want to send it to a completely different output. So I could see both of the things being true, if that makes sense. Where
yes,
it's possible that broadly, that if you're doing very dumb routing, you are actually better off making sure that that similar things go to different places. And then as soon as you get to smart routing, it will maybe 90% of the time be true that you want similar things in similar places because you do the exact same computation. And then once you get very good at it, you will start splitting off very similar but different and important ways things onto different experts.
yeah,
Yeah, I would love to see how this scales
Yes.
actually.
So on this one, I think
I think
there's the difference between things that are tokens that are very similar and what you actually wanting to do with the routing function. So what the routing function is trying to do. Jeffrey Hinton has a really good lecture on this because he kind of came up with the original idea of routing. But the thing that you want the router to do is not pick everything that's the same token coming in. You want to pick things that need the same computation being applied to them. So in other words, things where the function like x to f of x is like the same rather than where x is the same.
Right.
Yeah.
Yeah.
I would think that intuitively that makes the most sense. That hash routing works at all makes that seem questionable. Just because
Also,
it's
yes.
like if that were strongly necessary all of the time, right? This wouldn't work at all. Not at any scale, not even at the scale in the paper. This should break everything. So it can't be always the case that that's very important, because otherwise this would essentially have blown up the MoE completely.
So I don't think necessarily, but I don't understand what you're saying. I think there's one other thing that's going on here, which may be relevant, being that if you have completely different tokens coming into the same thing, same expert, then you can do clever things with like superposition, and you can have different subspaces which are working pretty much independently. Everything's orthogonal, so that also works nicely as well. And so that's one reason why you want different tokens going to different places. But yeah.
Yeah, fair.
Ah.
I think it could also be interesting to, on top of dumb routing, add maybe I don't know, a similarity search to group experts, and maybe that helps. Where bigram falls short, or something like that. So you're going back to multiple experts per layer. Was it switch transformers that broke from that?
Yeah.
First in
Switch
of the newer
transformers is
technique.
Switch transformers is we were doing top K because there was an idea that you needed more than one expert to compare them, and we can just do top 1 with routing loss, and it works, right?
Right.
Which is counterintuitive to me, but it does work. So
Yeah. Well, again, like I said, I think that just comes down to spreading out the parameters. To me, that just it makes sense intuitively. I don't have anything to back that up.
I think
It's like what in a dense model, like you have way too many things in superposition at once, so you want to sparsify the model to like reduce the amount of contention within each chunk of
Yeah.
parameters. But also for some reason, grouping similar tokens together is making things too similar, and like you also want to diversify to some extent in order to have some exposure to superposition. Like these two ideas seem in competition.
Yeah. I think I suspect we will get to a fundamentally sparsity is all you need, basically, versus clever routing is all you need paradigm. I'm just not sure we are definitively there. I think right now we are in the clever routing is all you need paradigm, but I'm not sure that's actually correct.
I'm actually that's another thing I'm playing around with right now. I adapted Wanda, for example, to work with. Right now, I've just got it working with the NeoX based models. But lately, I've been thinking about how, if possibly, we could take a really wide layer and just break this down to on a per token basis. And maybe it's just going back to something as dumb as L1, to prune in real time, to get the benefits of sparsity, but also the advantage of a huge wide layer. And it's just literally just picking the parameters that make sense, make the most sense for that given token.
Makes
I'd
sense.
like
I
to see.
I think I caught like 20% of that. I do not actually understand what he said he was doing.
I sort of get it, but I think it ends up being very similar to this, right? Where if you have
Yeah,
one wide
in a
layer and you're
sense.
only activating some of it per,
Yeah,
I guess
well,
it might be more similar to their multi-hash actually, where you're using certain parts of certain sub-matrices basically per token.
yeah, I'm very new to all of this, so maybe I'm just reinventing 7,000 wheels
I
and going just way too convoluted with it. But for me personally, like I'm trying to approach it with take a wide layer, try to prune it in real time, as well as applying a MoE and a LoRa technique to it. So basically, just
Echo things.
yeah.
getting the advantage of just honestly trying to eliminate pre-training, and just taking the whatever random initializations work best for that particular token in that particular moment, train on that and split it off as an expert.
I
That's where
think
I hope that makes sense.
that it does sort of. I do think about reinventing the wheel. I think it's fundamentally impossible not to reinvent the wheel. That too many people have done too many things. No matter what you do, like Schmidhuber or someone did something like that in the 80s, because of course they did. And it worrying about if your result is completely novel is, I think, kind of up. Unless it's something that's been done
Yeah,
with like a decoder over only model in the last 2 years, whatever you're doing, even if it was done before in some context, you're not actually repeating research.
yeah, I don't give a crap about being cited. I hope I am, correctly citing if I stumble upon something. Mostly, I'm just, I'm going after bang for your buck, as all of us
Yeah.
are.
Yup. Trying to get the most work done with the least pre-train. Okay.
If we're
I think
comparing the take of sparsity being like sparsity is all you need versus a really good routing is all you need, like
yeah.
I think sparsity just wins in this case. Like if you because the jump in improvement from having any form of MoE at all is really high, and
hmm
like the distance between the individual routing algorithms is like really small. Even though it is significant, but like it's still really small.
Yeah. It's relative to the no sparsity versus some sparsity. It's relatively
Yeah,
small. Yeah. I would, if I were doing it, I would lean towards something hash like at this point. Although people do have very good algorithms that seem to work rather better, sort of at a limit, right? If you're in a very high regime with a lot of data and a lot of parameters, it essentially and I guess if you're not going chinchilla optimal, you're trying to train for best performance period, like best inference time performance, because you're planning on inferencing it a lot. I can see the case that if you do, if you have to do 1,000 very complicated things with four different auxiliary losses, but it squeezes out an extra, I don't know, 0.05% perplexity, that might actually be worth it for your use case because you want as good a model as you can get at any cost. Like anything you can do to squeeze more performance matters. So I would expect at some point that when you're looking for like asymptotically ideal perplexity, you would get to a point where you know that a certain routing regime is the best regime, right? You know for a fact that like either you should or should not be doing complicated, basically very complicated routing or essentially randomly assorted routing. But yeah, I guess that's also where scaling falls off for these experiments, because they could hypothetically have scaled more of it, and later tests that say that this doesn't work very well are at much higher scale. Just
yeah.
if anything is a weakness of those experiments, it's that hash routing isn't really one thing. Like there's a lot of different variables that you could work with, and it's not clear to me that those are well explored, like dictionary size and whether you do one hash or multiple hashes across layers. So, for example, the unified scaling laws result where they compare hash against sbase, if it's because it's much higher scale, if it's hash with each token sees the same expert index at every layer, I would be very curious if that scales very differently at their scale compared with hash with a different expert index at every layer, with essentially a different hash function for every layer. Because it seems like that might be fundamentally better, where the difference is small at this scale, but could be very large at high scale.
Yeah,
But
but
because I don't know, if this is the
yeah,
baseline hash implementation, I don't know
like,
that it's
but like,
necessarily the best.
but like, because like while you're thinking about trying to improve the situation by going with different hashes per layer rather than the same hash per layer, I'm thinking about like what are the hardware efficiency gains you can gain like as a result of having the exact same hash for every single layer. And like what one cool thing that I think is possible with having the exact same hash is like if you're running a model locally and like you're loading it for inference, you can load one like expert for every single like token for every single token is generated. Like if you just start with a pure beginning of sequence token, then you only need to load the experts just for that token, and then you have that amount of time to load a new set of experts for next potential token.
Oh yeah, for sequentially, yeah, for
Yeah.
essentially each autoregressive pass, you only need one set of experts, or yeah, one set of experts, and you know exactly which one. I think you could get that even with different experts. Okay, so I guess so if you're loading it from disk, basically you can load it as an array because you have them all sequential. You have them all stored sequentially, right? Expert one for each layer is each laid
Well,
out end
I
to
guess that
end.
doesn't really matter with an SSD.
I think
It can matter. Yeah, go ahead.
I was going to say that I think that RL was saying that the part of the benefit would be that you don't have to wait in series to figure out which expert you need.
Yeah.
So you can preload the next expert because you already have the hashes pre-computed.
Yeah, but I mean that's true for either like whether you
Yeah.
use the same hash
I
for every layer or a different hash
Yeah,
for every layer, as long as
I
you're
guess
hashing based on
functionally the benefit might just be not recomputing the hash, which is a pretty cheap operation.
yeah.
You don't
So I can see it for, I guess not where you were originally thinking of it, but I can see it actually for sequential data storage if you're very memory or essentially IO or RAM bound. That sequential storage or sequential retrieval is always much faster than random storage, than random access. So if you have all of your experts for index 1 in one sequential block and all of your experts for index 5 in one sequential block, so if you're actually reading it out of RAM or reading it out of disk to load it, it will be much faster if you do that than if you have to skip ahead constantly because you're doing expert 1, then expert 7, then expert 43, right? Because you have to essentially do a seek each time, whereas sequential reads are always blazingly fast, like unbelievably blazingly fast especially off of disk, but out of RAM too. Nothing like skipping around, everything like sequential reads. So effectively, if you make your experts an array instead of making your experts sort of a random grid that you have to jump around in, you do get, I think, in a lot of regimes, you get a faster loading benefit.
The thing is, this works out for the toy example I gave of just starting for BOS token, but like in 99% of the cases, you're going to start from prompt. That prompt is going to have several tokens, and you're going to have sufficient token diversity that you want to load off the experts at once. Am I wrong about this?
This is usually correct. I think
Uh,
that will usually be correct on your first pass. On your autoregressive passes, it will not be correct.
no, but
So
you need to recompute everything in like each new autoaggressive pass. No, like
I think
the value of the value of each token embedding will be different as a result of the new attention that goes up between the new token and every other token. No,
it depends. It depends on, I think. So the actual, I think the actual
yes,
KV store, the KV store has some of it.
the only things that are saved are the KV store, but like
Yeah.
the output of the attention layer will be completely different, and that's going to
Yeah, that's true.
you need to recompute. Like,
Yeah,
that is true.
right.
Okay.
don't worry,
I think we might have run this down.
yeah, that should be it.
Cool.
Is Sumo in the voice call? I thought he was going to be the one to present next week, but if he's not here, then
You can ask him, he might still be around.
does anyone else have a paper in mind that they'd like to present? I ask this every week, but okay, answer is a no. The hope that I want to achieve, like at some point in some of the interleaving weeks, is that maybe we can get Aaron Komatsky to present his sparse upcycling paper, because that would be really cool. But if we cannot get that, and if we cannot get any other presenter for the following week, then we can probably just pause it for next week. Unless yeah.
We might have run down most of the core papers in the area.
I mean, there's still as one thing that we really have not covered in any of the sessions is the implementation efficiency stuff. So like the Tutel paper or the Mega Blocks paper, like those are quite important for anyone that actually wants to implement an MoE.
Fair. We should probably ping Aaron if we want to get him to do it.
Ah.
I don't know when he'd want to do it.
Maybe he would just mute the whole thread. Okay, that brings us to the end of this week's MoE reading group lecture. I will end the recording here.